All right. Objectives today, you should be able to classify polygons based on their sides and angles, similar to what we did with triangles with scalene and isosceles and equilateral and all that type of stuff with all the angles and all the sides and all that. So we're going to do similar to that. The only difference is today we're going to do polygons, not just triangles. And we're going to find and use the measures of the exterior and interior angles of a polygon. Lesson 2.4, you learned the definition of a polygon. Now you learn about the parts of a polygon and ways to classify your polygons. So the definition of a polygon is a closed figure with straight sides and 3 or more sides, I guess. Closed figure with straight sides, 3 or more. So each segment that forms a polygon is a side of the polygon. So each red piece there is a side. The common endpoints of 2 sides is the vertex or a vertex of the polygon. So A and B and C and D and E are all vertices. And a segment that connects any 2 non-consecutive vertices is called a diagonal. For example, if we do B to C, that's just a side. So if we skip C and go to D, B to D is a diagonal, B to E is a diagonal. And in this case, we only have really 2 diagonals if we're going from the same vertex. I mean, you could draw it from A to D and E to C and all that stuff, but if we're going to draw diagonals, we're going to draw them all from the same vertex. So really, there's only 2 diagonals in this. Any vertex you pick, you're only going to be able to draw 2 diagonals from it. Okay. You can name a polygon by the number of its sides. Here's a few of them: triangle, quadrilateral, pentagon, hexagon, heptagon, octagon, nonagon, decagon, dodecagon, and then anything above 12 is called an n-gon, or whatever the number of sides are, gon. So if there's 15 sides, it's a 15-gon. Okay, literally you put 15 here in place of n. If n is 20, you put 20-gon. That's what the side of the polygon is. We're mostly going to deal with these, not anything more. We might deal with them in the number fact of how many sides they have.
So in this list, there's no 11, so would we do 11 gon?
Yeah, and there is a name for it, I think, but I don't know it exactly, and we're not going to really deal with that. We probably won't even deal with the 12s very much. It'll mostly be maybe up to a decagon is usually what we deal with. And we'll learn some stuff about polygons that will make things easier, and we won't have to deal with their numbers quite as much. So a polygon is a closed plane figure formed by 3 or more segments intersect only at their endpoints. They can't go past the vertex. They can't be open, and they can't have rounded sides, and they have to 3 or more. So tell whether the figure is a polygon. If it is, name it. So this is a polygon. They're straight sides. They're closed. They don't go past their vertex. I mean, they touch at the vertex. That's it. They don't go any further. And it has 6 sides, so it's called a hexagon. So yes, it's polygon, and it is a hexagon. Is this a polygon? Absolutely. Are all straight sides. They all touch at the vertex. They don't overlap. They don't have rounded sides. It's not open. So yes, that's a polygon. And then we just have to count the sides. So we have 1, 2, 3, 4, 5, 6, 7. Okay. So that is a heptagon. Doesn't look like a normal heptagon, does it? But it's really a polygon, and it is a heptagon. This is not a polygon. It has rounded sides. And I guess in reality, it only has 2 sides, I guess, if you got real technical, and it needs to have 3 or more to be a polygon. So it's not a polygon. Can't name it. I want you guys to do the check it out 1A, 1B, and 1C on the bottom of page 394. Determine whether those are or are not polygons. And if they are, name them. All right, let's take a look at these. First one, this one is not polygon. It's open. Does have straight sides, but it's open. This one is a polygon. All straight sides, all meet at the vertex or at a vertex. And it is not rounded, all of that stuff. So then we just have to count the sides. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. Looks like 9. So it's a nonagon. 1C, no, it has a rounded side here. It's all closed and they all meet at a vertex. It looks pretty good other than this one rounded side. So that one's not a polygon. Questions on those? All the sides are congruent in an equilateral polygon. So if we talk about equilateral polygons, you're going to hear the word regular used. The word regular means that the polygon has equal sides. So if it's a regular pentagon, all the sides are the same. If it's a regular hexagon, all the sides are the same, 6-sided. Regular octagon, regular decagon, whatever it might be, it has equal side lengths. So technically an equilateral triangle would be a regular triangle. A square would be a regular quadrilateral, which we don't call it a regular quadrilateral because we have names for those. We have equilateral triangle, and we have a square. But technically the word regular means the exact same thing as an equilateral triangle or a square. All the sides are equal. It also has equiangular. So a regular polygon has congruent sides and congruent angles inside of it. So the angles that are in the triangle are all congruent as well. If a polygon is not regular, it's called irregular. So a regular polygon is both equilateral and equiangular. So you'll hear the word regular used a lot. A polygon is concave if any part of the diagonal contains points in the interior of the polygon. If no diagonal contains points in the exterior, then the polygon is convex. A regular polygon is always convex. Normal polygons that we see are convex. Okay? Concave is when you have one of the sides that, or one of the vertices that dip back inside. Like if you had like a funky looking kind of dipping back in, then that becomes concave. So concave is when you have, like I said, this kind of this funny section that dips back in the interior. This is a diagonal technically because it goes from this vertex to this vertex, obviously skipping the one vertex between them, which is what you have to do. That is a diagonal, but the diagonal ends up being on the outside of the figure, so that's called concave. Convex quadrilateral or convex polygons, they look normal. What you and I would say would be a normal polygon, those are concave, or convex, excuse me. Concave, if you think of concave as being caved in, it's kind of what happened to the polygon. One of the sides kind of caved in. Tell whether the polygon is regular or irregular. Tell whether it's concave or convex. So the first thing is regular, irregular. Remember, regular has to have equal sides and equal angles. Does this have equal sides and equal angles? It doesn't. It has equal sides, but it does not have equal angles. These two are equal and these two are equal, but are they equal to each other? They are not. So this is not regular. This is irregular technically. It's very close to being regular, but it's not. And then is it concave or convex? One of the sides is not caved in. We don't have any diagonals that would be on the outside. So we would say it's convex. Irregular, convex. So irregular and regular is kind of tough. Because this looks like a nice quadrilateral. It looks like a nice, but it's not a square. In order for it to be regular, it needs to be a square. That's it. You can't have a parallelogram maybe as this is or stuff like that. Tell whether the polygon is regular or irregular. Tell whether it is concave or convex. All of these angles are the same, but are all the sides the same? Nope. So it's irregular again. And is it concave or convex? Well, if I go from this side to, or this vertex to this vertex, that diagonal is on the outside of the figure. We have a caved in piece. So that would be concave, irregular, concave. This one, we have 4 sides that are equal, and we have 4 angles that are equal. Technically, it's a square. So is that regular? Absolutely. That's a regular quadrilateral, or what we call it as a square. And is it concave or convex? It's normal. It's not caved in. It has normal diagonals in the interior of it, so it's a convex polygon, regular convex. All right, do the check it outs. 2A and 2B on page 395, please. Tell whether it is regular or irregular, and then tell whether it is concave or convex. Regular, irregular, and then concave or convex. All right, first one, irregular or regular. The sides are all the same, awesome. The angles are all the same, awesome. So that's regular. That's a regular pentagon, technically. And then is it concave or convex? Well, there's nothing caved in. We don't have any diagonals that go on the outside of the polygon, so that's convex. Regular, convex. Okay, remember to look at all the sides. If they're good, then look at all the angles. If they're good, that's regular. Okay. What that means is each one of these sides is the same length. Each one of these angles is the same degree, and we'll talk more about that later when we start finding that stuff. Regular or irregular? Well, we know the side lengths aren't the same already, so that's irregular. And convex or concave, this diagonal would be on the outside, so it's concave. So irregular, concave. Remember, all regular polygons are convex. You'll never have a concave regular polygon. Okay? Because the inside angles all have to be the same. To find the sum of the interior angle measures of a convex polygon, we draw all possible diagonals from one vertex of the polygon. This creates a set of triangles. The sum of the angle measures of all the triangles equals the sum of the angle measures of the polygon. So, a triangle, of course, we know the triangle has a sum of 180 degrees, or the interior angles of a triangle have a sum of 180 degrees. So this one's 180. If we have a regular triangle, which is also called an equilateral triangle, the angles are all 60 degrees because they have to add up to 180. If we have a quadrilateral, we can draw one diagonal in a quadrilateral, which cuts it into two triangles. If we have two triangles, then those angles have to add up to 360 degrees. This angle, and this angle have to be 180. This angle, and this angle have to be 180. And if we add all those together, that would give us what those interior angles would have to add up to. So every single quadrilateral should add up to 360 degrees, the interior angles. Like a square has 4 right angles, right? 4 times 90 is 360. That's the same thing for every quadrilateral. A pentagon has 2 diagonals, which cuts it into 3 triangles, which then again, we can take 180 times 3, and that gives us 540 degrees. So in every pentagon, there should be 540 interior degrees, or angles degrees. A hexagon. A hexagon has 3 diagonals, which makes 4 triangles. Again, if we take 4 times 180, we get 720 degrees. So inside of a hexagon, there should be 720 degrees in the interior angles. Are you picking up on a pattern here? If it has 3 sides, how many triangles are there? 1. If it has 4 sides, how many triangles are there? If it has 5 sides, how many triangles are there? Okay, so what do we know? The sides and the triangles are what? 3, 1, 4, 2, 5, 3, 6, 4. The triangles are always 2 less than the side lengths. So if you take the side length minus 2, multiply that by 180, it gives you your interior degrees. 3, 1, 4, 2, 5, 3, 6, 4, it just keeps going. If you have a 20-sided figure, it would be 20 minus 2, which is 18. And then you'd take 18 times 180. And that would give you how many degrees there should be in a 20-sided figure's interior angles. Okay, so that's why the n-gon or the 15-gon or 20-gon or 30-gon or whatever you're going to use. That's why it's important to at least know that, but all we have to do is multiply 2. We have 2 less triangles than we have sides. So, questions on that one? I think we've done that before. So, in each convex polygon, the number of triangles formed is 2 less than the number of sides. We just talked about that. So the sum of the angle measures of all these triangles is n minus 2 times 180. So however many sides you have, minus 2 times 180. Theorem 611 is the polygon angle sum theorem. The sum of the interior angle measures of a convex polygon with n sides is n minus 2 times 180. So you're just going to be able to subtract 2 from the sides, multiply it by 180. Find the sum of the interior angle measures of a convex heptagon. A heptagon has 7 sides, so we are going to take 7 minus 2, which gives us 5. Take that times 180. Oh, sorry. 1 too many. We get 900 degrees on the interior angles of a heptagon. Now, do we know what each angle is? We don't, because it's not regular. It doesn't say regular heptagon. If it was a regular heptagon, then we could figure out each angle by taking 900 divided by 7, and that would give us what each angle has to be for them all to be the same. 3B, find the measure of each interior angle of a regular 16-gon. So each interior angle of a regular 16-gon. So now we have to figure out how many degrees are in a 16-gon. And then we have 16 interior angles. So we have to divide whatever number we get by 16 to get every single one of them, each interior angle. They're all the same because of the word regular. It's equiangular. So all the angles are the same. So I first take 16 minus 2 and multiply that times 180, which gives me 2,520 degrees. Now, I want to know what each interior angle is, not just all of them added together. So now I have to divide that by 16. And I get approximately, actually, that's probably exactly 157.5. So 157.5 degrees is the measure of every single angle in that 16-sided figure, or all 16 angles inside that figure. Does that make sense? How to find the measure of a regular polygon, whatever it might be. In this case, a regular 16gon. Find how many degrees are inside it, and then divide it by how many sides it has, or how many vertices it has, and that'll give you the angle measure. Find the measure of each interior angle of pentagon ABCDE. So a pentagon, this is not regular, it's just a pentagon. We don't know the angles are all different, or could be all different. So what we're going to do is we're going to figure out how many degrees should be in a pentagon, and then we're going to add these 5 angles together and set it equal to that. So we take 5 minus 2 and take that times 180, we get 540 degrees. That means those 5 angles should add up to 540. So that's what I'm going to do. I'm going to add 18C, 32C, 32C, 18C, and 35C. Add all of those together. Gives me 135C. Divide both sides by 135. C is 4. That's not my answer. I have to find the measure of each of these interior angles. So if I substitute 4 in here, I get 35C is 140 degrees. The two 18Cs are 72 degrees, and the two 32Cs are 128 degrees each. So you should have 140, a 72, a 72, a 128, and a 128 measure for those angles of that pentagon. All right, do the check it out. 3A, 3B on page 396, please. First one, you just got to find the sum of the interior angles. 3A. Second one, 3B, you got to find each one. So that's a regular polygon. So then you can find the sum of the interior angles and then divide that by how many sides it has. All right, 3A. Find the sum of the interior angle measures of a convex 15gon. Again, you're going to take 15 minus 2, and then take that times 180. 13 times 180 is 2,340 degrees. And that's all we really needed here. We just need the sum of all of them. It's not a regular polygon. If it was a regular 15gon, then you could divide this by 15 and that would give you what each angle is, but it's not. The next one is similar to that. So find the measure of each interior angle of a regular decagon. So regular means it's equal angular. So we're going to take 10 minus 2 and take that times 180 to find the sum first, because I need to know how many degrees are in a decagon. And that's 1440. Because it's a regular decagon, I know that every angle is the same. So I'm going to take 1440 and divide that by 10. And that actually gives me 144 degrees for each angle inside that decagon. So you got to divide that by the number of sides. Don't divide it by 8. Make sure you don't go back to the decagon being 10-sided and divide that by 10. How many degrees will be in a decagon? Every decagon. Correct. Every single decagon will have 1,440 degrees in it. Every single one. Whether it's regular or not, that doesn't matter. It still will have the same amount of degrees in it. That's not going to change. Okay, so after you do a few of these, you'll notice like, well, they're just the same thing. Well, yeah, that's what's going to happen. If you have a hexagon and a hexagon, they still have the same degrees in them. They don't have any different just because they're different shapes or different sizes. They still have the same amount of degrees in them. In the polygons below, an exterior angle has been measured at each vertex. Notice that in each case, the sum of the exterior measures is 360 degrees. So every time you have exterior angles, all of the exterior angles will add up to 360 degrees. Every single time, no matter how big your figure is, all of them will add up to 360 degrees. As long as they're all, you know, the extensions off of each side, you know what I mean? If you continue to go around the circle or go around the figure there, those angles will always add up to 360. Whether it's a triangle or a pentagon here, in this case, they're the same. Okay, so always will add up to 360. So we have theorem 612, the polygon exterior angle sum theorem. The sum of the exterior angle measures one angle at each vertex of a convex polygon is 360. What it means by one angle at each vertex is you can't do both sides of that extension. Just do one side of that extension, the angle it forms with the side. Find the measure of each exterior angle of a regular 20gon. So again, a regular 20gon has equal angles, or the interior angles are equiangular. Therefore, every extension or every exterior angle should also be the same. Well, the exterior angles of a whatever should be 360 degrees. So if we have 20 vertices on this figure, then you have to take 360 divided by 20 because it's a regular 20gon and all of them should be the same. So a 20gon has 20 sides and 20 vertices. So the sum of those angles, the exterior angles, should be 360. So we're going to take 360 divided by 20, and we get 18. So every single exterior angle of that 20gon should be 18 degrees because it's regular. Another example. Finding interior angle measures and sums in polygons. So we're going to find the value of B. Now, these are exterior angles. So what we know about the exterior angles is they should add up to 360 degrees. So if we add every one of those, 18B, 33B, 16B, 10B, 28B, and 15B, together, we should get 360 degrees. So that's what we're going to do. We're going to set it up as a little equation here. We are going to add those together and set them equal to 360. And again, when we add them together, we get 120 B's, and we divide both sides by 120, and we get B is equal to 3. Once we get B is equal to 3, maybe that's all we want. We just want the value of B. But now we could find how many degrees each one of those are. 45, 54, 99, 48, 30, 84. We could find all those. Do the check it out 4A on NB, excuse me, on page 397, please. 4A and 4B. Find the measure of each exterior angle of a regular dodecagon. And find the value of R in that polygon there, JKLM. All right, let's take a look at these. 4A, find the measure of each exterior angle of a regular dodecagon. So we want each exterior angle. There is a dodecagon is 12-sided. So there's 12 exterior angles. They are all the same because it's regular. It's a regular dodecagon, which means that all of them are the same. So we're going to take 360 because we know the exterior angle should have 360. We're going to divide that by 12. So 360 divided by 12 is 30 degrees. So each angle, exterior angle, of a regular dodecagon should be 30 degrees. And the next one, find the value of R in this polygon. We know that these exterior angles should add up to 360. So we're going to add those four together, set them equal to 360. We get 24R equals 360. Divide that by 24 on both sides, and R is equal to 15. Then we could find the exterior angles here. You know, we could substitute that in and find those measurements if we wanted to or needed to. Okay. Questions there? Let's look at an example of application here. Anne is making paper stars for party decorations. What is the measure of angle 1? If we go around this, what is this figure right here? It's a pentagon, and it has congruent sides, doesn't it? So if they have congruent sides, the exterior angles all have to be the same. And if the exterior angles all have to be the same, and add up to 360, we could take 360 divided by 5, couldn't we? 5 sides or 5 exterior angles, 360, because this angle, this angle, this angle, this angle, and this angle are all those exterior angles that should add up. And they should all be then 72 degrees. So how big should angle 1 be? Should be 72 degrees. Has to be 72 degrees if it's a regular pentagon, which it is. It has the same side lengths there. What if you had, this is a shutter of a camera. The shutters of a camera close and open when they take pictures, of course. So the shutter has normally had 10 or sometimes has 10 blades here or 10 pieces that kind of collapse together to take that picture. So you have 10 sides on this guy. What would be the measure of the exterior angle if it was 8 blades instead of 10? So if you look at example 5, that one does 10 blades. The question is now, what if it was 8 blades instead of 10? What would that change? What would the exterior angle be then? Okay. So look at example 5. Do the check it out, number 5. Find what your exterior angle measure would be. Each exterior angle would be if you had 8 blades instead of 10. Okay, if it has 10, of course, example 5 showed us that they took 360 divided by 10 and got 36 degrees. That means all the exterior angles should be 36 degrees. However, if it had 8, we would have to take 360 divided by 8, which then would give us 45 degrees for each exterior angle in those blades. Questions on that one? I don't have any more for you. Your assignment is on the board. Do those for tomorrow, please. Quiz will be on Friday, last grade of the quarter.